with that, let's get started. Let me introduce Chinmoy Chakraborty, who's going to tell us about Q#, the Q# programming language.
Yep, absolutely. So are you able to see my screen?
Yes.
Okay. But I am not able to see you all at all. Maybe because I am.
So I don't think you need to be seeing us.
Okay.
We can unmute ourselves when we want to ask a question.
Okay, sure. So you see my screen, right?
Yes, indeed. Oh, wait, actually, what we see is your speaker view. So we see the slide that you're trying to present to us now and the slide that comes after it.
Oh, okay. So it's.
I think if you, I don't know what kind of machine you're using, but what you want to do is convince your machine that you have only one monitor. Oh, that looks good. Okay. Yeah.
Okay. Yeah.
All
Okay.
right.
Okay. Hi, everyone. Welcome to the session. And this session we'll be talking about Q# and QDK. Little bit about myself. My name is Chinmoy. I'm not a quantum physicist. I'm a technical architect in Microsoft, and I'm based out of Atlanta. And my primary focus is application development and application modernization. So when you think about microservices, Kubernetes, API management, service bus, event hub, I covered those areas. Nowadays, I cover AI and the GenAI space as well. So my quantum computing journey started around 3 years back when I was working for AWS. One person joined our team, and we got the welcome note from the leadership team. And in the interest section, that person mentioned quantum computing. So that's the first time I heard about quantum computing. Got interested in that topic. I did some research and joined a community in Amazon in the quantum computing. But after that, I joined Microsoft around 2022, and one of my colleague, he introduced me to Azure Quantum, and that's when I got interested in the quantum computing again and started learning about quantum stuff. There are great materials in Microsoft site. I'll send you the links. And this is where I am today. So I'm available in LinkedIn. I'll share the link if you wish. You can connect with me. So let's get started. The topic we covered today will give I'll give a quick introduction of Q#. We'll talk about the QDK, and we'll walk through some of the quantum compute program and hands-on kind of stuff. So Q#, maybe you are already aware that Microsoft open source programming language, and this is language. This is the language you can use to develop your quantum algorithms. And in quantum computing, you are not supposed to write, or build the circuits. Using the Q#, you can write quantum algorithms. Using the Q#. Q# supports the classical and the quantum computing integration. So if you're using Q#, you can integrate your quantum computing workload with this classical computing workload. And Q# is hardware agnostic, meaning that there are multiple hardware vendors that Microsoft offers. For example, IonQ, Quantinum, Rigetti. These are the different hardware vendors that Microsoft support. Once you write the code in Q Sharp, you can run that code in any hardware Microsoft provides. Okay. And QDK is a quantum development kit. So Q Sharp is the programming language. QDK, Quantum Development Kit, is a full-featured development kit for Q Sharp. It provides the libraries for Python languages. It provides the resources, tools, and the libraries for Q Sharp. It provides the libraries and the packages for Qiskit and Sark. If you don't know, Qiskit is a Python-based language for IBM quantum computers, and Sark is the Google language. So using that QDK, you can write code in Python, .NET, Qiskit, Sark, any of your preferred languages. QDK has a plugin for VS Code or Visual Studio. And once you install that plugin, you are good to go. QDK offers some resource estimator. And resource estimator is very, very important, right? Because in real life, when you will be running your quantum algorithms in actual quantum computer, it might require millions of qubits. But before you run those algorithms, you want to know that, okay, what is the cost of running this algorithm? How much space and the qubit resources I need to run this algorithm? So it will give you a measurement of, thousands, how many thousands of qubits you need, or millions of qubits you need, and things like that. So QDK, yeah. Any question? So QDK offers those resource estimator, and you can run code on any quantum hardware. So the components of Q-sharp program starts with a namespace, quantum operations, types. You can allocate qubit, you can measure qubit, and it offers different libraries. So it is standard stuff, but only differentiating factor is allocating qubits and measuring the qubits. So this is a sample Q-sharp program, and if you can see here, this is the namespace, this is the entry point, operation. So this, I'll talk about this namespace, entry point, operation, and this is the allocation of the qubits, and this is how you are releasing those qubits. So these are the different parts of this Q-sharp program, and I'll show the actual code in a moment. But before I show the code, these are some of the key concepts of Q-sharp program. Namespaces are used to organize your code. In the Q-sharp, we have namespaces, but it does not support nested namespace as of today. Entry point, this is a spatial attribute. It tells you the entry point of your code. Okay, so the program, I'll show you, I'll point out this entry point, which means that's how the execution of those algorithms or of the code happens in the entry point. And this is a QSub command you need to try if you are using any Python packages. Okay, I'll show you some of the Python code samples as well. But this is just FYI. These are the different types: standard stuff, double, Boolean, string. And this is how you can allocate qubits. as I mentioned before. Um, this is the way you can use qubits, and this is the way you can perform any operations. H gate, X gate, you can put into superposition using this H gate or Hadamard gate. You can use any other gate C naught to entangle two qubits. But these are some of the examples how you can allocate qubits. These are the operations. Means it's in other languages, it's like a function where you are a block of code that performs certain tasks. Those are called operations. And this type declaration is like any other languages. I'm going through this kind of concepts quickly because it's almost same with other languages. Comments, double slash. Iterations with the for loop and standard conditional loop like if and all that. So you have this conditional loop as well. This is also standard with the .NET thing. Conditional branching, logical expression or not, standard stuff, arithmetic expressions. I'm not going through all these slides over here. I'll go through only this memory management piece. This is the important one. So in a normal programming language, we all do heap calculation, right? Heap management, allocating memory for this programming. So the qubit, allocating qubit and releasing qubit is just like your heap management. Okay, when you want to allocate some of your task in the qubit, you just allocate a qubit, and you can allocate multiple qubits, and you can release those qubits when you are done. So allocation qubits and the releasing qubits is just like your heap management in other heap memory management in other programming languages. I will switch to the demo now. So far, any questions? Okay. So you can start with this quantum.microsoft.com.
Hello.
I will. Yeah.
Hi, can you hear me?
Yeah, I can hear you.
Yeah, no, I'm just chiming in right now. I did have a couple questions earlier, but for some reason my microphone wasn't working. Can you tell me a little bit about the relationship between Q# and the IPython kernel? How does that work?
So this is okay. Since you asked this question before, I mean, I plan to show you later.
Oh, in case you're going to answer it later, then we won't worry about it now.
Okay, I'll come to this. I'll come to this. Okay, so any other question, Barry?
One or two went by while my microphone wasn't working, but I'll think of them later. Thank you.
Okay, no worries. So
this is the place. I have a quick question.
Yeah, sure. Go ahead.
So you mentioned that Q# is an open source language.
Yeah.
Is it interpreted or compiled?
I think it is interpreted, and the
so
qubit.
Is the interpreter open source also?
Yeah, everything about Q# is open source.
Great, thanks.
And the QDK is also open source. QDK is written in Rust, I believe, but that is also open source.
Just a quick question, Chinmoy.
Yeah, go ahead.
Are you going to cover the architecture of the programming language also What I fail to understand mostly is about how in the world the superposition really, gives the outcome that we look in our general programming or in the programming language.
Okay, so whatever this program I'm about to show you, it uses the simulator, okay, to simulate the quantum operations. I'll show you some code which runs in the browser, so that the simulator is simulating those quantum operations. Having said that, you can run this job in actual quantum hardware as well, okay? But as you know, that right now, whatever the quantum computers are available today, those are very noisy, and your result might not be same as the simulator. But I'll show you how you can submit those jobs to the real quantum hardware. Is that answer your question?
No, that sounds good. Yeah, we'll see. Yeah, yep. No, thanks for this.
Okay.
Chinmoy,
So
a few
yeah,
minutes
go ahead.
ago, we got a question in the chat. Where is the block statement in the slide you're showing? I don't know which slide that refers to, but if there's a block statement that you can go back to.
Okay, let me see. Uh, this is the comment one.
That was the
Iteration.
slide, the quantum memory management slide is the one.
Okay.
Okay.
Mm-hmm.
And the block looks like it's the,
This is the one.
yeah, in the for statement, right?
Yeah, absolutely. So um, the restriction, the only thing which I think worth noting is that there is a restriction. The type of qubit always starts with no qubit, and the values of one qubit type cannot be passed as an entry point arguments. Okay, so the value of one qubit cannot be passed for another qubit. That is the restriction we have today. And this is intentional. So if you allocate a qubit and perform some operations and you expect certain outcome from one qubit, you cannot pass that the value of that one qubit to the another. That's the restriction we have. But the qubit allocation is similar to as managing your heap memory.
So again, I'm reading because I think Neil's microphone isn't working. Fortunately, mine is working now. He says the text refers to block statements defining the scope of the quantum memory. Where is that block statement?
Block statement means, I think, I don't think there's a block statement. It's a block structure. And it needs special parameters because of the no cloning theorem, I would guess, which is what you were talking about. You can't share the state of a qubit with another qubit.
Right. Exactly. Okay, we'll
I have
go
a
to,
question.
yeah, go ahead.
You said that the Q sharp is an interpreted language. Does it interpret to the same intermediate language as C sharp does?
On the interpreter, I have to take that as a follow-up. I'm not sure. about how the Q-sharp interpreter works, or I do not have the architecture diagram, but I'll take that. I'll take that as a follow-up, and definitely I'll let Barry and you all know about this Q-sharp interpreter in more
Okay, I have
details.
a couple other related questions.
Yeah,
So,
go ahead.
is it a just-in-time thing, and is there a compiler at all?
This is again, I have to double check,
Okay.
but I believe this is just in time. That's what I feel, but I need to double check and confirm how
And
that interpreter works.
what platforms does the interpreter run on?
Um,
I mean, I assume
Again,
it's executable, and so does it run on Linux, on, you know, obviously it runs on Windows.
yeah,
It runs inside of VS Code, right?
yeah. So there is the the simulator what we have, it has, when I run this in the browser, it hits to some server, but it's not in the JavaScript or whatever. You can run this program in multiple places. I'm going to show you how and how many ways you can execute this program. But there are some simulators running some server. It goes there and executes that block of code there. So I'm sorry. I mean, all these interpreter related question, I need to double check, and I'll get back to you all with the details how the interpreter works, and what are the platform it runs upon and things like that. Any other question?
I think we're okay for now.
Okay. So this is the place where you can start with to learn more about Azure Quantum, and then you can start with the quantum coding here, and I'll also put this link in the chat, and you can see this is an in-memory simulator. And this is a sample code. By the way, this is not static code. You can write any other code over here. And so this code is a hello world code. It just choose a random beat and checks whether it allocates a qubit, and then puts it into a superposition, and then measures it and puts that result. So this is a very sample hello world program, and you can run this program. And if we set the 50 shots, and you can run, and it executes in the browser. So as you can see, the result is almost 50-50, 50% one, or 51% one, 49% of zero. And the good thing is that we have these Copilot mentioned over here, and you can say highlight this code, and you can say explain code, and then Copilot gives you nice explanation of that code. This code allocates a single qubit. So whatever the simulator built in here, you don't need to install anything. This is in the browser, and you can use Copilot to explain any code and ask any other question and things like that. So it suggests other questions. You can click of any of these questions. It will answer your question and give you a sample code. Now, if you want to go a little further, this is icon over here for the VS Code. You can click this icon and it opens the VS Code in the browser. And it takes whatever I had in here and opens up this editor on the browser. You can use this ID in the browser, or you can use your VS Code locally as well. These are the ways you can run your Q# over here, and this is the way you can also debug. In my case, I have installed VS Code, and I'll switch to the VS Code running locally in my machine. So I have now switched to my VS Code installed in my machine, and the extension I have here is QDK. So as you can see, this is Azure Quantum Development Toolkit. I have installed that. You need to install this Azure QDK if you are working with the VS Code locally, and then you can run this code. So this is the code that generates a random number and within 0 to 50. And if I run this program, I say .NET run. So now it gives me the result 30. And if you debug over here, I have debug point over here and here. And if I start debugging and go to here, and it stops in my debug point. And if I just step over, as you can see in this quantum state, I mean, in the real quantum atmosphere, obviously you cannot measure and see the result, but since this is running on the simulator, it will give you some feel that how the value is changing, and you can debug and track all the variables over here. Okay.
So can you tell us what the difference between let and use is? Is use specific to a data object that represents a qubit?
I didn't get your question. What is the question?
So your line 43, you have use keyword. And it looks like, to me, it looks like you're setting
Yes.
a variable. And then on 53, you have a let statement, which is classic in a bunch of languages. What's the difference between let and use? Is use specific to quantum qubit space?
So as this says, this is the syntax for allocating a qubit in, say, Q#. Okay.
Okay.
Now you can allocate another qubit, say Q2.
But well, I guess my question, you have to use the keyword use, USC,
Yes.
to allocate a qubit, and that's all.
Correct.
That's the only thing you use that keyword for?
Correct. Exactly.
Okay, gotcha. Thanks.
Yeah.
Hello, Chinmoy.
Yep.
I have a quick question.
Yeah, go ahead.
I know that there's a classic library, a Python library called Classic that's specifically for quantum computing. The syntax is very similar to Q#. But my question is it possible to automatically convert Q# into Classic? Do you have any type of technology that does that?
That's a great question. I have not tried that myself, but you can try GitHub Copilot to convert that.
Are you talking about Classic?
Yes,
C-A
classic.
with IQ at the end?
CLASSIQ.
IQ. Okay.
Yeah.
Yeah, they have their own language. That may look similar to this, but
It
it's
looks
not
very close to
Python.
this. It looks very,
It's
very
not Python. It's their own language.
right.
Yeah. So I am not sure if there is a way you can convert the Q Sharp code into Classic, but I definitely try Copilot, GitHub Copilot
Okay. Thank
to
you very
convert
much.
those. Yeah.
Thank you.
The reason I said that Copilot, because I see a lot of customers, they have their old, for example, stored procedure written in SQL query, and now they are converting those stored procedure into C# or any other languages. They are doing that using the GitHub Copilot. So that's the reason I said that you can try converting those, but I have not tried that myself. So far I tried Qiskit, Sark, and Q Sharp, and some of the Python packages, but you can definitely try. Okay.
So one more question. In this
Yeah, go ahead.
example, where did you define the back end, or did it default to a simulator?
Yeah. So in this case, this is default to the simulator. I have not yet submitting this job into the actual hardware.
Okay, thanks.
Yeah. And then you can run this. Sorry. And get the result. Now, if you are interested to submit this job into the real quantum hardware, so you need to go to this quantum workspace here. And I have a quantum workspace created in my Azure subscription. So let me show you that quickly. So this is my Azure portal. And in my Azure portal, I have this quantum workspace. And I have created one quantum workspace, ATL Quantum. And that is what you see here is ATL Quantum. And if you expand this ATL Quantum workspace, there are two things, providers and jobs, okay? If I expand these providers, you see these are the different quantum hardware provider that is available today. IonQ, Microsoft Quantum Hardware, Quantinum, and Rigetti. So in Rigetti, Anka 2, this is that actual quantum hardware, okay? So I tried today morning a couple of times to submit this job into this real hardware, but I got some error. But definitely you can try this in order to submit this job, this code to run in the actual quantum hardware. I can try one more time and see what happens. It still gives some of the error, but these are the different hardwares it's supported for the IonQ. You see IonQ, this one is the simulator, but IonQ QPU ARIA 2, this is the actual quantum computer where you can submit the code to run. And in the jobs section, once you submit your job to these providers, you will see all these jobs executed in the actual quantum hardware. But as I mentioned, the simulators do not have the noise simulated. Okay, so you get the actual result, and you can see if I run this this kind of programs, say generate a random bit, right? 0 and 1, almost 50% time it generates 0, 50% time it generates 1, close to 50%, because that's a simulator. But if you run in your code in actual quantum hardware, you might get a different result because of the noise. Okay. Next, what I want to show you is that you can use resource simulator. In order to do that, you can create a new, say, sample.qs. So QS is the extension of the Q# programming file. And sample.qs, here, if you just type sample, you can see all these samples that is available. You have Shor algorithm, Grover's algorithm, and all this kind of stuff. But if you start dynamics, so it gives you, this is the sample quantum code. It's not a very little complicated code, and what it does is it simulates an Ising model, Hamiltonian, on N1X, N2 2D lattice. I really don't know what it does. As I mentioned, I'm not a quantum physicist. I don't understand, but this is a little complicated program that you have the sample code for. And you don't want to execute this code in the simulator because you don't know how much memory it will take to execute this code, and how much compute you need, how much memory you need. And you prefer to execute this code in actual quantum hardware, right? Now, before you run this program in actual quantum hardware, you want to know that what is the resources you need in order to run this program. So in order to estimate the resource, you can go to the common palette and this calculate resource estimate, and you can choose different qubits over here. So I'm going to choose this NS-E3, E4, and Floquet code, this one and this one, 4 types of qubits I am choosing. And then I am just setting my error budget, 0.333 or whatever, 0.334. This is the error budget. And I say the sample name is dynamics. And it gives me very nice report that how much physical qubits I need in order to run this algorithm. So the first one, as you can see, it requires millions and some thousands of qubits in order to execute this program. And this is the space, and the runtime is 315 milliseconds and almost 2 million qubits. For E3, if I go A6 Floquet, around 205,000 physical qubits and 55 milliseconds, it gave you a very nice chart to give you an overview about the runtime and the space. Okay, the space is the number of qubits, and the time is how much time you need in order to execute that program. Now it will give you some other details as well. This is the space diagram, and it provides you all other important details for the quantum researchers. They will be interested in this kind of information. For example, if I go to this resource estimate breakdown, arithmetic qubits, algorithm depth, clock frequency, number of t-state, t fractions. So it gave you all these details before you run this program into that actual quantum hardware. Because running your program in actual quantum hardware, there is a dollar amount attached to that. So before you run this actual program, you need to have an estimate that, okay, how much it is going to cost to run this program in the quantum hardware. This gives you this physical resource estimate, logical qubit parameters, T-factor parameters, and things like that. So it gives you tons and tons of information before.
How do you map this to dollar amount?
So at this point in time, there is some cost calculator. I don't have the link, but I'll find out the link. I'll just send the link to you all, and you can go to the cost calculator and put these numbers. This is my physical qubits. This is the qubit name, and this is my runtime, and it will give you some kind of an estimate that, okay, this is you need this much of cost in order to execute that program in the quantum hardware. We have some cost calculator for other Azure resources.
Isn't it kind of pointless if it's saying you need 1 million qubits though?
Yeah, at this point in time, yes, it is, because the biggest quantum computer we have that supports, I think, 11,000 qubits. IBM has those, but the biggest, this one in our quantum workspace, IonQ, Quantinum, Rigetti, these are the hardware supports maximum 100 qubits today, not more than that. We are working towards this quantum computer. We are making a lot of progress. I don't know when we'll hit the 1 million qubits. Maybe 2 years from now, 5 years from now. I don't know the timeline, but you are absolutely correct. We don't have millions of qubits in any quantum hardware today, but you can be quantum ready and you can get an estimate before you run these algorithms in actual quantum hardware.
Chinmoy,
Yeah.
these codes that you have on the screen, when you run them, do they actually run on top of a physical quantum computing, or is it a simulation?
Yeah, that's what I mentioned. You can definitely try running in the simulator, but I really don't know how much memory you need, how much compute you need in order to simulate this Hamiltonian,
As a simple guideline for a simulator, you need 2 to the n plus 4 bytes. I'm sorry, 2 to the n plus 4 bytes, where n is the number of qubits. So if you want to simulate 30 qubits, you need 2 to the 34 bytes of memory. It gets up there very quickly.
Yes. So you can try running this program in the memory, but as you mentioned, I forgot your name, sir, but you can calculate the memory size, the heap size, and the compute before you run this program in the memory. That is why I mentioned that you prefer to execute this kind of program in the actual quantum hardware. You can try submitting this job to any of the actual quantum hardware today and see how it performs. I did not try yet, but I plan to. Maybe in the near future I'll try to submit this exact code in the actual quantum hardware and see how it performs. But I'll stay away from running this program in the simulator today.
If I may, I am just asking a simple questions because I have no idea about this. Why would somebody write anything in the quantum program language? Why would you not use a other program language? I know there is a speed to it, but what is that?
Yeah, so as you know already, in the classical computer, there are some limitations, right? We cannot simulate the nature in the classical computer. There are reasons why we need quantum hardware to simulate nature because of um, the complexity and the time heap memory size and the compute it takes. For example,
How did it compare with NVIDIA? Like, I'm just trying to understand, because most computing thing that we do right now is on the AI side, right?
For example, let's take example of source algorithm, right? In source algorithm is basically entire RSA cryptography based on the finding the prime factors. So today, all our computing technologies are safe because if anybody wants to break all those 130, 128-bit key, it will take infinite time to
I think
break those.
I know about that. Thanks so much. Yeah, no, it's complex problem that it can solve. Not good for simple problems. Yeah.
Yeah, so that's when you need to solve quantum computer to solve those kind of problems. Having said that, quantum computer is not good for every kind of problem. Okay, so the common question is quantum computer is going to replace the classical computer? The answer to that question is no. In fact, quantum computer is going to integrate with the classical computers, and by which we can get the best of both the worlds. Some of the stuff that classical computers are good will keep utilizing those classical computers for those kind of things. For example, AI and the Copilot and all this kind of recent development, right? This is good for the classical computers. Continue to use classical computer for this kind of activities, but in the field of chemicals and the material science, when you are simulating a particular molecule or try to find out some new molecule and things like that, then you need quantum computer to simulate those kind of environments. Okay.
Before you leave this, by the way, I didn't introduce myself. I'm Ron Schreiner. I'm one of the organizers of this meetup. And I forgot to mention thank you to Barry Bird for making this happen. Can you scroll up a little bit so I can read the entire prologue to this thing? Oh, you're going down.
Okay, scroll. So this is the start of the program.
Yeah, I see line 8. What's above line 8?
Line above 8.
Is there anything above line 8? Because I can't see it. Oh, you know what? Actually, it's probably a display problem on my side. Never mind.
Okay, so before line 8.
There we go. I got it. Okay.
Yeah.
Okay, thanks. I'll read that's good. So there's much more to this algorithm than just that main function, right? The rest of the file defines the icing model. Okay.
Yep.
All right. Thank you.
Yeah. And the last thing I wanted to share. So once you have the quantum workspace here in the quantum workspace, and then if you go to this Jupyter notebook and open that Jupyter notebook, it will you'll be landed here in your Azure quantum workspace in Azure portal. Okay, and here you can use this notebook, and these are the Python packages. This is how you take a handle of the workspace, and then from here you connect to your workspace, and then you can see these are the different quantum hardware that is supported by Microsoft today, IonQ, QPU. So I showed you how you can utilize this in your Visual Visual Studio Code in your local machine. But if you prefer to run this code in notebook, you can do that from the Azure Quantum Workspace. And here you see this Area 1. This is a real quantum hardware, not a simulation. And you can submit your job in this actual quantum hardware and see how it behaves. And here you can import Q-Sharp, and here you can run the whatever the program you want to execute. And this is a little visualization you can see in this quantum notebook. So you can see almost, since this is a simulator, the result is absolutely 50-50. 50% of the time it generates 0, 50% of the time it generates 1. This is a program that generates a random bit, 0 or 1, and this is what you see in this visualization. So there are some samples gallery over here. And this is the Qiskit one, this is the SART one. You can explore other samples, and you can copy this Qiskit one. The moment you say copy to my notebook, you get that sample over here, and you can try executing your code over here in the quantum in this notebook in the quantum workspace.
Is there just another quick question? Is there a real life case or use case that that is like, offered by the Azure's quantum computing, the learning thing, that we can go through to understand how does it really take the real world scenario and then
real world scenario, I have one which is let me see,
that helps to relate of what we are doing, technically versus why we are doing it.
So this is the VS Code Quantum Playground, and I have some examples over here, Bale states and all these entanglement. This is
that's still more not a real world. It's sort of like, programming for the quantum computing concepts and ideas, right? But let's say you were giving an example of something in the material industry or in the nature. There is a problem to understand or simulate some sequence of genes or whatever that might be, right? So having to understand that real problem, and then how do you really achieve that through the quantum computing? I'm just trying to understand if there are something out there that I can refer. That's pretty much it.
I am not sure.
Could I suggest that we hold off on these large questions until after the presentation, because they really are huge questions, and we might get a good discussion going.
Okay. So this is an implementation of source algorithm, but yeah, it's not the real life use case. But you can see if I want this to find out the prime factors for 143, you can go through this entire program to understand more about the Q-sharp syntax and things like that. It definitely helps you to understand the language. But again, this is not simulating any molecule or material science problem. It's not. These are the samples that are available today. But if I have any real life programming samples, definitely I'll pass on that to you. Okay, so that ends my presentation. That's all what I wanted to share with you today. And now, if you have any questions, now the floor is open for the questions and the discussions.
Are there questions? I have a few. I guess there's one here on the chat. Is there any good GitHub code to try out for this?
GitHub repo?
Yeah, that's. I'll read the entire. Is any good GitHub code to try out for this? At least within the simulator memory bound for common personal classic computer for now. Could you share this piece of code sample.qs as well?
Yeah, so let me share this. I mean, this is the starting point. You can start here. And I also share these samples as well.
So for those who don't have access to the chat window, in case that doesn't show up, there is quantum.microsoft.com en-us/experience/quantum-coding. And the other is vscode.dev/quantum/playground. Just thought it would be good for me to read those out.
Yeah, so if you go there, you will find all this sample code. And here in this quantum.microsoft.com, it must have some GitHub, GitHub samples. Okay, I'll share the GitHub sample URL as well. So I just shared the GitHub repo URL for the quantum samples.
Yeah, so IBM's Qiskit world has tons and tons of stuff up in GitHub. They used to have a pretty good online tutorial. It's a little bit difficult to find these days, I've been told, but hopefully it's still there. But they give you pointers to the GitHub repository. So everything that's been presented today has to do with what are called gate-based quantum computers. And this is the real benefit to learning how to program a gate-based quantum computer is to learn how to do them. The fact is right now that we don't have quantum gate-based computers that are big enough to handle problems of a certain size that would make it worthwhile. I think you mentioned you thought IBM has an 11,000 qubit machine. That would be news to me. I haven't heard about that yet, but I know they were working on somewhere around 1,000 qubits at some point. But and I also heard that they realized that they have to come up with a whole new architecture for their superconducting based qubits. But it should be pointed out that gate-based quantum computers aren't the only kind. We have gate-based algorithms can be run on superconducting junctions like IBM, trapped ions like IonQ, and I don't know what Microsoft and Rigetti run, but I assume they're all similar, superconducting Josephson junction based thingies. but there also are trapped ions, and there's
Yeah.
also quantum annealers, and they have abilities to do things beyond gate-based things. Right now, your best bet is if you need to show some business advantage. Right now, the money is on the quantum annealers, but unfortunately, that means you're only dealing with optimization problems because quantum annealers aren't complete quantum machines, but they excel at optimization problems. And
Yeah.
there's people out there making money doing this.
Right.
So, yeah.
So you're still at NISQ level 0. I mean, Microsoft claims that we are at the level 1 now, but still at the noisy level. The results are noisy. We are working to make those outcomes stable. Microsoft actually did a breakthrough 1 month back, and that's why Satya mentioned that we are at NISQ level 1, not 0, because of the reliability. But we are going there. I don't know when we'll have the reliable quantum computer.
Yeah, if you're talking about IBM or Microsoft's announcement or co-announcement with, what was it, IonQ or Continuum?
Mm-hmm. Yes.
Yeah, they've come up with a way to create 4 logical qubits
Yeah.
at very high resilience, but there's nothing you can do with 4 qubits.
Yeah.
Yeah.
And about your IBM comment, Ron, I think the biggest computer IBM had is 433 qubits. But in last December or January, I saw somewhere they released a paper or something that they got quantum computer. I mean, more than 1,000 qubits, almost 10,000 or 11,000 qubits. That's all I remember.
Yeah. So the 433 is, I believe, their code name is Condor.
Yeah.
And the next bigger one is just about 4 times that size. But that's the last I heard. But I mean, but they could have moved on, but they don't seem to be publishing as much anymore.
You're going to get there, Ron.
They will. Somebody will.
I have faith.
I have my money on the neutral atoms, though. Right now you can get access to a 256 qubit neutral atom machine produced by QEra, and it's online. The only way you can get to it, though, is through Amazon, or is through is it Amazon Braket service? But that particular computer doesn't run in gate mode. It runs in a quantum analog mode, which is a bit different. But you can get really cool things done. You can get hard problems done over there too.
Yeah.
But yeah.
What you all are researchers, quantum researchers, quantum physicists, or what you all's background?
I think we're all different backgrounds.
Yeah, I'm mostly mathematics, electronics, and science, not so much on the quantum mechanics. Okay. I've just been blessed to fall into quantum and make a whole bunch of successes stories out of it. And I'm actually working as a quantum consultant for a pretty big company.
Awesome.
Yeah, and we're making progress with the quantum annealers. We're getting business problems solved with it. So
yeah, we Microsoft has some customers like BASF and other some customers in UK and Europe. They are creating a virtual lab to simulate some of their molecules and stuff like that. and all these customers are getting quantum ready,
Yeah.
by which when the actual quantum computers are available, they can utilize those machines as soon as possible. Um, so that's the primary use case today that we see with the companies and the customers.
So Ron, were you saying that Q sharp is applicable to like the quantum annealers, or is it just a matter of developing support for it?
I don't know Q sharp. That's why I'm here to learn about it. But I get the feeling that it is pretty entrenched in the gate-based domain. So the algorithms are for quantum annealers are formulated completely different. It's actually a lot of math and exploiting this beautiful concept called binary quadratics. And again, they're only good at optimization problems. They don't run generic quantum algorithms. But this is why business likes it, because everywhere you go in business, people want to optimize stuff so they can save money.
So what do you mean by
Yeah.
So John mentioned that John wants the sample.qs code to share. So John, if you open the VS Code, either web or in your local, and just type dynamics, and then click those the dynamics link, you will get the code. Or I can send you the file as well. Here, let me try to attach that file if I have the permission to do that.
We can do that offline. You can send it to me and I can send it to the attendees for this meeting later.
Okay. Yeah.
Yeah. Good idea.
I get one of the questions I've been having is I see the reason to use this environment that you're showing us, the things that you can do while you're running in the Q sharp environment. But why as a language is it more expressive or better at expressing quantum concepts than, let's say, Qiskit or some other language? Is there a compelling reason for me to learn Q sharp in terms of understanding the way that quantum computing algorithms work?
So Q sharp is just a language like Qiskit or Cirq, okay? But the real benefit comes with the QDK, okay? Quantum Development Kit. And it's a platform that offers you all the libraries and packages, not only for Python, but for Qiskit, for Cirq, for Q sharp, all one-stop shop for all your quantum programming need. Now, you will go towards the C sharp or Qiskit or Cirq. It's your personal preference. But it's like Java or .NET or whatever. It's personal preference. The one thing about the Q sharp is that it integrates well with the classical computer and the quantum computer. So you are trying to achieve a particular task. If you think that some portion of it you can use our classical computer to do that, you just do that. And the part or the job you want to submit to the quantum hardware, you can do that in a single piece of code. I mean, single file, right? So that's the integration, I would say, is the main driving factor for me to use Q sharp other than Qiskit and Cirq.
And does it integrate with Qiskit and Circ by some low-level language tricks, or does it import those libraries in some other way?
So I mean, the QDK, so Q Sharp is the language, QDK
Right.
is the programming platform. QDK has the support for Qiskit and Circ. Okay, so QDK has all those tools and libraries to use in the, yeah, go ahead.
Just to be clear, though, Qiskit is not a language unto itself. It's a Python framework.
Yeah. Python based.
And I believe Circ is the same. I would
Yeah.
have to double check that. They're not languages unto themselves. But it looks like Q Sharp might be at least a modification of C Sharp.
Yeah.
Yeah.
You're right, Ron. Qiskit and Circ based on Python. There's a Python packages, and then there is a wrapper on the top of the Python packages that makes the Circ and Qiskit.
Yeah, and somebody was asking about what is it interpreted into or compiled into. So like if you're picking IBM as a backend, or actually most of the gate-based operators support CASM, the quantum assembly language, which is a very terse low-level. It's fairly terse low-level language. It's just like assembly code on a CPU back in the day, and so you just translate your whatever source code you have and translate it into CASM, and then CASM can be executed directly on most of the gate-based platforms. I know it's the case for IBM, and I believe it's the case for Rigetti. I'd have to check on the other ones, but it makes sense if you got a gate-based machine, it makes sense that you would be able to run CASM code. But CASM is not very low level. There's no structure to it. It's basically linear instructions. It's like the old days of writing assembly code for a Z80 instead of writing it in C.
You got to start somewhere.
Pardon?
You got to start somewhere.
Yeah.
Ron, could you?
Yeah, I think Jonathan shared that link where IBM collaborated on 10,000 qubit quantum computer.
Yeah, they committed to a collaboration. They haven't achieved it yet. They plan to do it by 2029.
Okay.
Ron, could you explain more what you mean by optimization? And is it something that the gate-based machines will never be able to do, that the annealers can, or is it?
Oh no, the gate-based machines will I believe they'll definitely be able to do it, but it's just because we don't have the width. We don't have the high qubit counts in the machines, like IBM's Eagle, which is 127 qubits, and the Condor, which is 433. Based on their topology, these things are so wide that getting qubits on each corner of the die to talk to each other basically makes it impossible to run any algorithms at depth because of the poor topology. But if you had a large qubit or a gate-based machine with 1,000 qubits that had really good interconnectivity, had a really dense topology, I'm sure you could run optimization stuff, but you'd have to write it from the gate-based standard. Quantum annealers leverage again this beautiful mathematics of binary quadratics, and they have this they use quantum phenomena to basically shake the result you're looking for. It's out of the system, and that they're called annealers because they cycle the energy on all the qubits. But so we're using the vendor D-Wave, and they claim that their current machine can handle 5,000 constraints. But it's a hybrid, so they use their annealer alongside quantum machine or classical machines. But these things solve really, really tough problems in 8 10, 15 seconds. Things that take classical machines a much longer time to do, even if you got a nest of GPUs to back them up. So
Sorry,
Yeah.
I'm
the typical problems like the traveling salesman,
Yeah.
any
Mhm.
number of graph-based problems like minimum independent set, max cut. You know, if you've got a graph that's got 100 edges in it, you're completely outside the ability of classical to do anything but use heuristics and guess at it.
Okay, so by optimization, sorry, you have to forgive me, I'm a little novice to this. Optimization is calculating tasks like the traveling salesman.
Yeah, so the object of the traveling salesman problem is to find the shortest route. And the only way that we know that you can do that for sure is brute force on classical.
Mhm.
Having said that, there are classical algorithms that will use heuristics to make really good guesses. Whereas the quantum annealer basically solves this by simultaneously checking every possible route. It's not the same as parallel. It's using quantum mechanical phenomena to simultaneously test every possible route in one operation. And that's a lot to get your head wrapped around. I don't think I still even have my head wrapped around it. I can only tell you that we get results out of the machine that almost always outperform the classical heuristic approaches.
Yes, and another use case would be like or cryptography, right? As a source algorithm mentioned, finding the prime factors for a large number. If
Yeah,
you
so that's definitely in the gate-based wheelhouse.
Mhm.
However, there is an annealer version of it that attacks it a little bit differently. It basically runs the multiplication problem backwards
Mhm.
because in quantum land, all of your operators, your gates or your things have to be bidirectional. They have to be reversible. So if you build a quantum circuit on the annealer that looks like the digital equivalent of a large multiplier, you basically on the annealer run it backwards. It's a completely different approach than Shor's algorithm, but you basically run the multiplication backwards,
So,
and
Ron,
it somehow gets you a number.
how close is annealing to cracking RSA and spoiling everything for us?
You still need way more because again, even though they do 5,000 constraints, the
Yeah.
number of digital gate equivalents to make a 1024 or 512 by 512 multiplier is a whole bunch more constraints. Yeah, so, but they may get there first. I don't know. They're working on bigger machines and faster machines too.
Are they doing better than what we can do with gate-based machines? We can factor 21, right? That's been the
Well,
best.
I think I read the largest one that's been factored on a real quantum machine using Shor's algorithm was the number 237 or something like that.
Really? Okay, that's
And
better.
yeah, that's going back a ways, but again, who knows how much time they spent on it, how many because of the noise, how many times do they have to run it? But you know, and that's pulling out all the stops and spending all the money you have really to do 237 or whatever the number was. It's not very impressive at all, but
We have other questions. Questions from other attendees.
So Ron, when do you think that we'll have a million qubit computer in the market available for people to try? Just a guesstimate, you know.
I wouldn't even begin to guess. I can tell you that I was recently out in Boston a couple of weeks ago, and I was able to visit QEra and actually walk right up to and stare at their neutral atom machine. They are on track to have a like by 2026 a 10,000 neutral atom based, a 10,000 qubit neutral atom based machine online and working in gate based mode and analog mode and having the ability to support logical qubits. So
Wow.
that's moving fast. And there are people building in academia or research labs, there are people building really large neutral atom machines, but like in the order of 10,000 neutral atoms, 20,000 neutral atoms, but they use a different technique for suspending the atoms that makes it difficult to put. I mean, it makes it difficult for them to put the atoms to work, but there's so much progress going on neutral atoms. I'm still going to stick with that as probably being the technology that makes the big breakthrough for gate-based stuff.
Yeah.
And again, neutral atoms, they can do annealing sort of too. So who knows? But millions of qubits, I wouldn't even want to. I would just be pulling something out of the sky. I would have no idea.
Yeah, and in the Microsoft, I know one team is working towards the quantum networking. You know, so in our classical computer, we have the stack, right? The 7-layer stack. So they are working on the quantum networking stack, by which they can connect two or more than two quantum computers together.
Yeah,
So
that's the holy grail, and the big bottleneck there is the no cloning theorem once again. So you can't transfer the state. You can't copy the state from one machine to the next. You can transfer the state from machine A to machine B, but you can't copy it. So but there is research going on where people are starting to claim that there might be ways to get a feeling for the state of a qubit without actually measuring it. I don't quite understand any of that yet, but that could be a possibility. I think the biggest thing in quantum networking is it's going to be quantum key distribution. Being able
already
to,
being
yeah,
tested and even marketed maybe.
people are making money with that as we speak, and it have been for some time. And this is again based on the fact that once you read the state of a qubit or of an atomic particle, you can detect that it's been tampered with, because there's a way for you to detect that somebody read the thing while it was in transit, so you can figure out a way to securely transfer keys from over large distances now. Actually, I think the Chinese have demonstrated that using satellites.
Yeah. Yep.
And that's pretty impressive. I was really hoping something like that would come to the US. But in the US, instead of using satellites, they're using optical fiber networks to do quantum key distribution. I think the first company did it was basically all they were doing is sending keys across the Hudson River from one stock exchange to the next, so that there was no chance that anybody could intercept those keys.
Do we have other questions? Well, it's getting late here in my time zone. Chinmoy, I want to thank you very much for your presentation. I'm going to have to pull myself away from the languages that I've been using and try out Q# again. I tinkered with it years ago, never got back to it, tried some of the katas, and life got in the way. You know how that works. But I've got to get back to it and work on it, especially in some of the features that you showed us tonight. Everybody who's in attendance, everybody who listens to this online, please remember that on July 30th, Scott Aronson will be with us. He'll be doing a Q&A session. And he promised me, he told me that he's not interested in preparing any slides. He's not interested in preparing any talk. He just wants us to ask him questions. I am happy to do that. And I urge you all to post questions on the meetup page so that we have lots to talk about with Scott Aronson on the 30th. Chinmoy, again, thank you so much. Thank you to everyone for attending. Good night.
Thanks, everyone. And I will share the sample QS file and other artifacts with you, Barry. And please share those with the community as you feel appropriate. And thanks, everyone. It's a great pleasure talking to you. As I mentioned, I'm not a quantum physicist. You all are very well read and already know about this quantum field more than me, and I'm still learning. So thank you all.
Thank you.
Thanks again, Barry, for making this happen. I'll be in touch.
Okay.
Thank you.
Thank you, guys.
Thanks, everyone. Bye.